This video lecture is meant to cover the information found in section 9.1a, which is on rate laws. A rate law is a mathematical equation that relates how the change in concentration of the reactants to the rate of the reaction. So, for example, for the reaction A plus B turns into C. The rate law looks like this. This is a generic rate law. Rate is equal to the rate constant K times the concentration of A raised to the power of N times the concentration of B raised to the power of M. Products are not included because it is the reactants that dictate how fast the reaction will happen. Okay, so K is the rate constant. Bracket A is the molarity of A. Bracket B is the molarity of B. N is the reaction order. Basically, it's the exponent for reactant A. M is the reaction order or the exponent for reactant B. And then, of course, the rate is the speed of the reaction. Okay, so this rate law right here must be determined from data. From your data table. There's going to be a data table with trials 1, 2, and 3, and you're going to have to compare those different trials. So the must be determined from the data. The coefficients of the balanced equation do not matter. Okay, so we're going to take a look at the examples that are on your review sheet questions. Question number 4 says the following data was obtained for this chemical reaction A plus B turning into products. We see experiment number 1, 2, and 3. We see the initial concentrations of A, the initial concentrations of B for each of the 3 trials, and then the initial rate of formation of the products in the final column. Okay, so what you need to do is to find 2 trials where A is constant. So if we take a look at trials 1 and 3, we see that A is constant, and we see that B doubles. Okay, so from trials 1 and 3, we see that A is constant, but B doubles if you consider, if you're starting with trial 3, compare it to trial 1, the concentration of B doubles. So the question is, for the concentration of B, if it doubles, right, and you raise that to some power n, that has to be equal to the change in the rate between those 2 trials. So from 0.4 up to 1.6, that's a quadrupling. So what, if we doubled B, that's this number right here, what power do we need to raise that to in order to get a rate increase of 4? Right? So there we see that that n has to be 2, and we call this the second order. Okay? So from that, we start with our generic equation. Rate is equal to K times the concentration of A times the concentration of B. We just saw that by doubling B, that will then double the reaction rate. So the order of 2 is the exponent on the B. Right? But now we have to take a look at 2 more trials where B is constant. Okay, so that would be trials, let's see, 1 and 2, right, where B is constant. And what's happening to A in trials 1 and 2? The A is doubled, we see. So if you're going to double A, right, so what power do you have to raise that to? What does that do to the the rate? Well, in this case, from trials 1 to 2, it's only a doubling of the rate. So 2 to what power gives you an overall rate increase of 2? Well, in this case, this has to be first order. So we see an exponent of 1 right there. So that right there is your rate law for problem number 1. Okay, let's take a look and see at problem number 5. We see that the following data were obtained for this chemical reaction, A plus B turning into products, right? Just starting with the basic rate law, rate is equal to K times A times B, and our job is to figure out those exponents. So let's see, we're going to find the first 2 trials where A is constant. So if we take a look at trials 2 and 3, trials 2 and 3, A is constant. And what is happening to B in those 2 trials? B is doubling. Oh, incidentally, right here, the corrected values for the initial B, you may or may not have an updated copy of this, but this number here should be 0.15 and this number here should be 0.15. So if it isn't, if it says anything else, please change your values to those numbers before we proceed. All right, so we're looking at trials 2 and 3 right here. A is constant, but B is doubling. So if B is doubling, that would be 2. Doubling is 2, of course. What power do we need to raise that to see this change in the rate? Well, the change in the rate is not changing. There's no change in the rate, right? So that we're not going to have any multiplier there. So 2n is equal to 1. So in this case, n is 0, because 2 to the 0 power is going to give you 1. So this is the 0th order, which means there is a 0 exponent on the B. All right, it's just going to basically be multiplied by 1. So we'll update that here in a moment. Well, we'll do it right now. So if this is B to the 0, we just wouldn't even include it. It just disappears because multiplying by 1 makes it disappear. Right? So now we need to look at 2 different trials where B is constant. B is constant between trials 1 and 3. Right? So B is constant there. And then what's happening to A in that case between trials 1 and 3? A is tripling. Okay, so that means we're increasing it by 3-fold, right? So between trials 1 and 3, what's happening to the rate? Well, from 0.4 up to 3.6, that's 9 times. So if we're tripling A, to what power do we need to raise that to get an overall rate increase of 9 times? So here we see that n has to be a squared function. All right, so that's what we call second order. All right, so basically that right there is your rate law, K times A squared. All right, there's one more question that we need to look at. That's number 6. Consider this reaction, Q plus X turns into products. They're giving you the rate law, K times the concentration of Q times the concentration of X to the 3rd power. Okay, so that's the first order right there, and that's 3rd order on the X. So what's going to happen if you double the concentration of Q? If you double the concentration of Q, 2 to the 1st power, what's that going to do to the overall reaction rate? Okay, well, 2 to the 1st power is just 2, so doubling the concentration of Q will increase the reaction rate by a factor of 2, so it'll double it. All right, doubling the concentration of X increases the reaction rate by what factor? Well, here, let's say we keep Q the same. Let's say we're not going to change Q, but now we're going to double X. What's that going to do to the rate? Well, 2 to the 3rd power is 8. So doubling X will actually have an increase in the rate by 8 times. All right, that's it for reaction rates and rate laws. We'll see you back in the classroom.